Tonight's presenter is Dr. Jessica Schonhut-Stasik. Or Dr. Jessica is a postdoctoral scholar at Vanderbilt University specializing in galactic archaeology, which is the observation of stars as fossils in our galaxy to investigate the formation and evolution of the Milky Way. Originally from the UK, she immigrated to the Big Island of Hawai'i in 2015, where she completed her master's at the University of Hawai'i before commencing her PhD work remotely with Vanderbilt University. She graduated with her PhD in May of this year and moved to Nashville shortly after. Congratulations, by the way. During her decade in Hawaii, she observed with some of the largest telescopes in the world atop the mountain of Mauna Kea and worked for 6 years as a telescope system specialist at the United Kingdom Infrared Telescope, logging over 250 nights of solo observation time. She is also a neurodivergent self-advocate and holds the position of Director of Communications at the Frist Center for Autism and Innovation, which is housed in the Vanderbilt School of Engineering. And then she is also the CEO and president of the Neuroverse initiative, which is a nonprofit that utilizes research, training, and advocacy at the intersection of neurodiversity and space science to support neurodivergent space scientists in the U.S. In the U.S. to thrive. So please welcome me, or please welcome me. Yeah, welcome me. Go ahead and welcome me. Please join me in welcoming Dr. Jessica Schonhut-Stasik.
Thank you. Ooh. Hello. Oh, it's working. My bio got longer and it's tiring to hear it now. I feel like I should not do all the jobs I do. Okay, let me make sure my mouse is in the right place. It is! Perfect. Okay, so I was going to introduce myself, but I need not, which is brilliant. Dr. Jess is fine. My last name's a bit of a mess. But as Billy said, I worked on Mauna Kea for about 10 years. I reached Nashville I moved here in June. I love it. Do miss Hawaii though. And I came here to do my postdoc. So when I was thinking about what to talk to you guys about tonight, I thought about my research, which is cool. It's cool. You know, galactic archaeology is a emerging field. Maybe I'll come and talk to it another time. But then we thought, actually, maybe people here don't know a lot about Mauna Kea. Living there for so long, I kind of forgot that it's not totally ordinary. So we're going to talk a bit tonight, or at least I'm going to talk a bit, about, I did not do these transitions. Canva is AIing them, and I love that. Hopefully they stay good. So there's a bunch of things that Mauna Kea is specifically very important for, and astronomy is only one of those. So I am mostly going to talk about the science on Mauna Kea tonight, but also what Mauna Kea means for discovery. So that's using that science, utilizing it, and kind of making these really groundbreaking discoveries. The majority of our largest astronomical discoveries in the last decade are from Mauna Kea. Although, okay, maybe I'm biased. But also Mauna Kea as it relates to culture and as it relates to the future of astronomy, because we can't have astronomy, we can't have science without humans, right? And really, we set what we're going to do in that future. So I'll talk a bit to that, but mostly we'll do the science. Okay, so let's talk about Hawaii. Who's been to Hawaii by a show of hands? Whoa, okay, well, why am I here? Who's lived there? Anyone? Okay, who's been to Oahu, so like Honolulu? Ooh, sorry. Who's been to Maui? Good choice. Big Island? Okay. All right. So we know we have some Hawaii knowing in the room. This is just a map of Hawaii, obviously, with the Big Island there at the bottom. For those who don't know, Hawaii is a 200 minimum island chain that is in the Pacific. It's actually the most isolated inhabited landmass in the world. I'm dry. Isolated landmass in the world with population. It's like a bit. There's others that have, fight for this title. And it is made up of, the inhabited islands are Hawaii, Maui, Molokai, Lanai, Oahu, Kauai. Ni'ihau is inhabited, but it's purely designed for indigenous Hawaiians. Not designed for, it's purely kept for indigenous Hawaiians. And the three biggest volcanoes on this set of islands are Mauna Loa, Mauna Kea, and Haleakala. So I'm talking a bit about those before I get onto Mauna Kea. Hawaii was and is a completely volcanic system. It was all made from the seafloor in a volcanic ridge. So by oldest to youngest, you start at the top left and move your way down. Hawaii Island is the youngest of the islands. There is actually a new island happening. It's just a bit, it's going to take a while, I think, just off the bottom coast there. It was going to be called, I want to say Luihi, and now it's being called something else, which I can look up if anyone's interested. But it's going to be, just down below Mauna Kea, just down below the Big Island there. So the three big volcanoes here. So all of these volcanoes are dormant. Well, not Mauna Loa. These two at the top are dormant. All that means is they haven't erupted in the last, up till 10,000 years. After 10,000 years, you can do extinct, but it takes 10,000 years. Which means that in theory, they could erupt, and they're both still tied to their magma in some way. So, but it's not going to happen. Mauna Loa, on the other hand, does erupt. Erupted a couple of years ago. I lived. The house that I have is in Volcano National Park, so just there, below there. I live about a 5-minute drive from Kilauea Summit, Kilauea Volcano, which is the one that you really need to worry about. But luckily, I live above it. Gravity's good like that. But unfortunately, on the slope of Mauna Loa. So when it went off in 2022, it was a question mark about which way it was going to go. And fortunately, it went not towards my house. It went towards Saddle Road, which would have been bad in a different way. But it was fine. It was fine. So Mauna Loa, Mauna means mountain in Hawaiian. Mauna Loa is the long mountain. So it's one of the biggest volcanoes. It's the biggest shield volcano as far as I know. And actually, one of my favorite kind of fun facts is that if you put Mauna Loa next to a scientific image of the other massive shield volcano, they look exactly alike. The other massive shield volcano is not on Earth. Does anyone know where it is? Mars. If you put Mauna Loa, an image, next to Olympus Mons, they look almost identical. But Olympus Mons is 100 times bigger, which is mad. So Mauna Loa is very cool. There are some telescopes on Mauna Loa, but they're mostly DoD, like privately owned or small. And I suspect this is because Mauna Loa does erupt, but it's also not as high up. So then we're going to skip Mauna Kea for a sec. Haleakala is on Maui. And does anyone know what Haleakala means? Anyone old enough here to remember the Animals, the band? What does Haleakala mean? Oh, no one? House of the Sun. Not House of the Rising Sun. Hale is house. And who's singing? Will. So Haleakala is famous for its observations of the sun. So all the most famous solar observatories are on Haleakala. I could maybe tell you a bit about some of them, but that's not really my area. Deakest is the most famous one. It opened, I want to say maybe 5-6 years ago now. And that's the premier ground-based solar observatory in the world. Haleakala is really cool because the way that the turbulence in the atmosphere, or lack of turbulence in the atmosphere, moves around the volcano means that if you put your thumb up over the sun in the daytime, it'll completely obscure the sun. Like, it won't make it dark, obviously, because the daytime's bright, but you won't be able to see it. Whereas I'm sure don't really do this, but I'm sure everyone's gone out and like done that, and you see the little kind of coronary vibe around the sun. That's the atmosphere. It's different up there. It's beautiful. Okay, so Mauna Kea, the White Mountain, because it snows up there. It's at 13,800 feet is the summit. This picture here is actually of the true summit. So this is no building on this. This is the kind of sacred area of the summit. It's all sacred, but this is that area. And then to your left, you see these little kind of pillars. These are lights that lead up to the observatories. I did ask my husband this morning. It actually was snowing up there last night, which is the first snow of the year. But I looked at the webcams and it's not like settled, so not very fun. I was going to show you, but whatever. So Mauna Kea is where the majority of our telescopes are. There are 13 although give or take, there's a whole bunch of information about that. But I've put 3 telescopes up here because anyone can be an astronomer, and that's what I love. And I wanted to take a minute to share. Any amateur astronomers in the room? Yes, love it. People with telescopes, loving telescopes, yes. Without amateur astronomers, there would be so much less, or so many less, I should say, astronomy discoveries. There is a lot of space up there, but there's very few professional astronomers. And the amount of amazing discoveries that have come from backyard telescopes blows my mind every single time. So I wanted to put a little, that's not a celestron, I don't think, little backyard telescope up there. So that's the first kind of telescope that a lot of people use, right? And then the middle, you've got the summit of Mauna Kea, all of these telescopes. These are the domes, obviously, not actually the telescopes, which we open up day and night to observe. And then on the far right, you've got Hubble. So that's our space-based telescope. A lot of those as well, very much different uses. And if anyone's interested in, like, why do we still have these giant ground-based observatories? I can answer that question later. The space ones are cool too, though. Okay, so why do we need big telescopes? I've tried to put in, but anyone who's been to the Big Island, did any of you go to the summit? No? Oh, what's this? Yeah, right. Oh, you did? I thought you were like, maybe, I don't remember. Like, I feel like you'd remember. So this picture on the right here is the Canada, France, Hawaii telescope. It's one of my absolute favorites because it really shows the collaboration between all the different countries that work on the summit. And a lot of my friends work there, so I like it. And you can see, it's not one of the biggest, but you can see the scale there. We've got some folks which are what we would call part of the day crew. So every telescope has a day crew. They go up in the day, and they fix things that break, because things break a lot, and make sure that everything is ready for an evening's observing. Of course, working at 13,800 feet is a lot. So there's a whole bunch of safety precautions and a whole bunch of things. You have to have multiple people up. You're not going up there on your own. You're always going to get scolded when you go up in flip-flops. Every time. It's very cold. It's also very, very cold. So, but why do we need the big telescopes, right? Why aren't we all just using these Diddy ones that you can buy for like $100 on eBay? We're going to talk a bit about that. Does anyone know? No. You can see more. But I'm going to talk a bit more information about that. So this picture is an amateur astronomer's picture of Andromeda, which is really cool, actually. Someone did a good job of this one. Color's nice, really nice, like kind of resolved. If you go onto Mauna Kea, you get this. Oh. Right, so this is from Subaru, which is Japanese-owned N-A-J-J-A-N something, which has a bunch of cool instruments. This was the test case for an instrument called HCS, Hypersonic Prime Cam, HSC. And it's really stunning, right? You can see that we just have that magnification and what we call resolution, right? So everything that we look at in the sky is going to have some kind of angle associated with it, which is from the angle from where we see it. And I'll show you that in a minute. But obviously, Mauna Kea, much better than our backyard astronomer. Finally, I'll show Hubble just because we have it. Even cooler, right? You can start to pick out the stars. You really can see the gas in there. Like, that is just a phenomenal picture. This one often gets used as like, this is the Milky Way. It's not. Why can't we have a picture of the Milky Way? Because we're in it. Okay, good. You're all awake. This is good. And also you see the little galaxy there that is getting sucked in, which I think is M104? I feel like you would know this, Will. I brought my friend Will along, who's very, very good at those kinds of things. I can't remember, but they're sucking in a little galaxy. So, resolution. These are 3 pictures of Nashville. The one on the far left is from space, apparently. I didn't know we had a picture of Nashville from space, but apparently it was like a big deal when it happened. I'm new here, I'm sorry. I'm sorry if that was like really obvious. When you look at Nashville from space and you try and find Broadway, can you see it? No, right? All the lights kind of jumble. Oh, there's a moth attracted to my lights. So, he likes the space one. So, if you look for Broadway, you can't find it. It's because all the lights have kind of messed up into each other, right? There's there's no way that you can pinpoint it. It's not clear enough. It's not resolved enough. And this is that angle I'm talking about, right? So when you're looking from space, there's this really large angle which you're trying to find something in, right? Not going to be able to see it. From a plane, can we find Broadway? Yeah, we can also find, everyone calls this the Batman building. I am lobbying it for it to be called Barad-dûr because it's way closer to Sauron in evilness, right? So, thank you, ma'am. I'm new, so I'm not sure if I meant to say that, but I feel like Batman's good, right? AT&T not so good, in my opinion. But you still can't pick out the individual lights, right? The final picture is of, can you find Broadway in this picture? Yeah, okay, there's actually a picture of Broadway, right? I just searched Nashville. I hope so, okay. It looked like Broadway. So all that to say is the closer you are to a thing and the wider your angle of resolution, the more you can make out, right? So what happens if you can't get close to the thing? You use the math, the only math, right? The angle that you've got here, you want it to be really small because the smaller the angle, the more you can pass out, the more you can resolve. And it's directly proportional to a bunch of other stuff, but what I'm interested in here is D. So D is the diameter of your telescope. And the larger that number is, the smaller the angle is. And that angle is known as angular resolution. The smallest angular resolution is the smallest thing you can resolve, right, on the sky. So if it's this big, everything in here will be like a fuzzy mess. But as you get smaller and smaller and smaller, you're going to start to notice individual things. Are you all with me? That was my first time using this analogy. I hope it worked. So the answer is, we need big telescopes because then we can resolve things further away. We can pass out different parts of a system, stars, exoplanets, etc. And these are all the mirrors from the telescopes on Mauna Kea. So all the big glass, we call it, on Mauna Kea is reflective. You can't make a refractor that big. We can talk about that later if you want, but lenses, it's not going to happen. So the keks are the biggest. They're both 10 meters. Each of the keks can be used together or they can be used separately. And they're kind of what we would refer to as like the biggest and kind of most effective visual to infrared telescopes that we have in the world right now, apart from the EELTs, which we'll talk about in a minute. Yucca, I'm going to talk about a bit because that's where I worked. CFHT was the one I showed you a minute ago. So that's 3.6 meters, right? So that massive telescope I showed you, that's like a third of the size of one of the keks, right? So these things are massive, which is, why we need mirrors. So why Mauna Kea? These are some pictures of the keks again. I'm going to leave you with while I drink some water, because it is dry up here, which is one of the benefits of being up high when you're using telescopes. Okay, so the absolute minimum that Keck cost, I actually don't know this off by heart, I looked it up. The minimum that Keck will have cost is $70 million. So that's a lot of money for a telescope, or back then it was. The first telescope was installed saw first light, I think, in 76 or 67. Keck came after that. But there's both the Kecks simultaneously looking at the Galactic Center. You make a big telescope, you make it super expensive, you make your mirror absolutely massive, but then you point it at a crappy sky, and you're not going to see anything, right? It's not going to matter. So why Mauna Kea for a telescope this big? Because your telescope is only as good as the sky it is pointing at, right? The atmosphere is a whole thing. And these lasers that you see are real, and all of the telescopes, bar, I want to say 4, have these lasers. And I can talk about why if anyone's interested, but that's, again, a whole nother topic in a bit. But I just wanted to show the lasers, didn't I? Where was I going with this? Only as good as the sky you're pointing at. Okay, so again, why Mauna Kea? Exceptional conditions for observing. So I already told you Hawaii is the most isolated, populated landmass. What's very cool about that is if you put a landmass in the middle of the ocean, the wind patterns and all the stuff in the atmosphere is going to just be kind of as smooth as you can get it. Like, it's not going to be perfect, but it's going to be smooth. So when you look up at the night sky and you see those twinklings of the stars. They're not really twinkling, it's the mess going on in the atmosphere, right? It's a lot of stuff all bashing into each other, there's clouds, and the more atmosphere you have to look through, the less precise your measurements are going to be. So again, you want a high altitude, did I spell that right? High altitude, 13,800 feet, perfect. Dry air, like I'm really dry right now. Dry air, less humidity, less turbulence, and dark skies. So there's actually some really nice dark skies around Nashville, I've learned. Not a lot of streetlights out in the country, which was great, kind of sketchy. I live somewhere with no streetlights and I'm loving it when I'm at home, but when I'm like walking the dogs, I'm like, so, but in Hawaii, all the streetlights are made of one wavelength. They're made of a sodium wavelength. So that's really cool because we know, if that comes up in an observation, you can get rid of it. But what I think is the coolest part of it is when people don't know. And there's kind of this orange glow in the whole island. And as you walk around, like you're in the Target parking lot, if you have something that's like orange or pink or in that waveband, it will just look like a solid color and people get like kind of weirded out by it. I gave a book to a friend many years ago, which was Animal Crossing themed. And they had some pictures on the front, all orange and pink. But when I gave it to her in the parking lot, it just looked like nothing. Like you just literally can't see it, which is pretty cool. It's really nice. But that's a good way to be able to have safety and dark skies. We want both. That's my pitch. Clouds. You can spend $70 million on a telescope and then a cloudy boy comes along, you're done for. So again, 13,800 feet, you're above most of the clouds. The clouds will drop, it's pretty cute, like if you get to go there and you get to see it, you'll see the clouds drop at about 4 p.m. It's to do with the relative temperature of the air. That's called the inversion layer. So that's where it flips over from kind of wet to dry. And it moves down throughout the day. So if you were to drive up to Mauna Kea for sunset, you would drive through the clouds. And that was one of my favorite things to do, honestly. And if anyone's interested in how you get up there and the safety precautions and stuff, then I can tell you. It is perfectly safe to go up. People go up to the summit all the time. People do silly things at the summit sometimes and have to get rescued. Don't go up in a sombrero and flip-flops. Like, I definitely have gone up in flip-flops, unless you are trained. Don't take a rental car up. They are not insured, even the 4x4s, right? You will be buying them a new car. This is the summit. So this is where all the telescopes are. This is a really old generated image. Some of these are, so like the CSO Observatory, that's gone now. The rest are still in use. So when you drive up, you see this road that comes down the bottom here. You drive up to about 9,000 feet. That's the visitor center. You acclimate, so you don't get altitude sickness. And then it takes about 34 minutes, if you're driving not precariously, to get from HP, Halepahaku, which is this base camp, to the summit. And going from 9,000 feet to 13,800 feet in 30 minutes is a lot, which is why you want to stop and acclimate. But some of the most beautiful views on that road you'll ever see. So you come up here and you can do this loop where you go round. One of the absolute best views, in my opinion, in the whole actual world is the view from the telescope I worked at, Yucca, which you see right there on the right. As you look out, you can see across through those two Keck telescopes right over to the ocean. And it's absolutely stunning. Okay, that's the precinct. Okay, let's talk about the Kecks a bit, because we all like the Kecks. So the Kecks are, two telescopes, like I've said. They can work simultaneously or differently. In this picture here, you can see some of the others, and you can see that relative size, right? Kecks are absolutely massive. So this mirror here, so the primary mirror here on the left of one of them, that's 10 meters across. And what's unique about the Kecks is they're made of segmented mirrors, which all fit together. And this can use a really cool system of kind of all of them move with little puffs of air, and that's a whole nother conversation to do with the lasers, and I'm happy to talk about it, but very, very, very cool technology. Replicated in JWST. So this probably, for anyone who's into looking at mirrors, this probably looks a lot like JWST in your head. One of the coolest Keck discoveries that's ever been made in my opinion. Does anyone know what this is? It's written at the bottom, so I kind of ruined it. But this is the I think this is the image that ended up getting the Nobel Prize, but this is the first real proof of the galactic center. Is that my phone? No. This is the first real proof of the black hole at the center of our galaxy was done with Keck. And you can't see anything in the middle of that image. So this is an image looking right to the center of the galaxy. You can't see anything because black holes are black. So they're dark, nothing there. You have to find them by inferring the movement of things around them. So each of these little circles is a star or some kind of bright body that's been orbiting around that center of mass over time, right? So this was taken over many, you can see here, 1995 till 2020. That's a lot of work. Each one of those dots is at the same time difference, if that makes sense, right? So you can see those dots on the left-hand side, if we're looking at maybe this pink one. Do I have a cursor on here? I do. This one is, look at this one. So all these dots are really close together, but the time between the dots is the same, the time between these data points. And then you see suddenly this data point and this data point, which tells you that it's very quickly moved. So as these things go like kind of, do you like my sound effects? And you can see this is the same for all of these, right? Like there's this big whoosh that happens around this spot in the middle. And what that tells us is there's something with a huge amount of mass and therefore a huge gravitational force in the center. So if you can't see it, it's got to be a black hole. And that was the first kind of conclusive proof of the supermassive black hole at the center of our galaxy, Sagittarius A star. And that was all done with Keck. Questions at the end, although I love it. I love the enthusiasm. These are some more recent Keck discoveries that I just thought were really cool because it shows the diversity of Keck as a telescope. The one on the left is Kepler 78b. So this was the first ever, first ever Earth-sized rocky exoplanet confirmed. So there's a lot of everyone here who's interested in astronomy probably knows that around every star we have kind of one planet is the average. And we're pretty good at finding them now, but confirming them and knowing what they are is an entirely different story. And Keck is basically, at this point, the only ground-based observatory that can actually image those, like can image at least some of sun or solar, stellar body and nearby planet. It can only do it for a few, but it can also confirm them in other ways using spectroscopy, kind of smelling the planet, or by using something called radial velocity, which is the movements of the stars and the planets. So Keck confirms a lot of planets, or arguably too many, right? We have a lot of papers about planets. We should just put them all into catalogs now, in my opinion, because I'm a star person. Gaia BH1. Keck contributed to the discovery of the closest black hole to Earth. I want to say it's about 10 times the size of our sun. And I want to say it's actually terrifyingly close, but I can't remember exactly how close. Another thing we may Google if you're interested. But very unique because it's not within the center of our galaxy. So those are two cool ones. I want to talk a bit about, let's talk about UCA. So this is my telescope. It's not mine, kind of. It's called the UCA, the United Kingdom Infrared Telescope. I am clearly British, but there's no connection. Like I didn't come to work there, I got hired after. UK didn't even own it by the time they gave up. They sold it we were owned by East Asia at that point. UCA is much smaller than Keck. But I think it's cooler for a number of reasons. One, it's in the infrared purely, which is a very hard waveband to observe in, and one that allows for some really cool science. Infrared allows us to do things like see through dust to what's on the other side. And any galaxy aficionados will know real dusty up there. Real dusty. So we were both the first fully remote observing telescope. This is me on the last night we spent at the East Asia Telescope. This was, like 7 years ago. My hair was so much cooler then. 7 years ago. So this is the monitor setup we had. So we were already fully remote at this point, but we were moving into moving under a different banner. So moving out of that office. And this is 1, 2, 3, 4, 5, 6. So there's 2 more monitors either side. And this whole system could run the telescope. But we we're at sea level, right? Which makes a world of difference. So this is the telescope that I observed. Yes, I actually, at the end, it was up to 300 nights of solar observing I did on this telescope in 5-night stints. So usually when you do this job, you do 5 nights on, 10 nights off, depending on the telescope, or 5 nights on, 15 nights off, just for safety, you know. And it's a long night, you know. Who's worked night shifts here in any way? Yes, yeah, right. Night shifts on a telescope, or like healthcare, which is also huge. Okay. Observatory, when you have those long winter nights, you're getting into the observatory at 3 p.m., you're leaving at 7 a.m., it's long. And then I was stupid enough to live an hour away, so I had to then drive an hour. But yeah, we were the first fully remote telescope, and I think that's really cool because it allowed us to become also the most scientifically productive telescope. So at some point we did I say at some point, continuously we have done all sky surveys in infrared. And those ended up being used in so many papers that we became the most productive telescope on the mountain, which is really cool, right? We created more scientific discoveries than I want to say any other telescope, or maybe even combined, to date. Still now. I looked it up yesterday. Very cool. And the part of this was the fact that we were one of the first telescopes to use what we call Q-based observing. So a lot of the classic telescopes, it's like Keck is a good example, will fly the astronomer out who wants to do the observation. You have to compete. It's like a big competition who gets time, right? They'll fly them out. That observer will go up to the summit with the person who knows how to work the telescope, and they'll do their bit of science, and then they'll come down and someone else will go. It's a whole like thing, right? With Q-based observing, all you need is me or someone else who knows how to work the telescope. Everything at the beginning of the semester just gets dropped into a computer, and the computer says, let's do these ones tonight. And then I go, yeah, that sounds good. And then you line it up and it does its thing, right? I mean, it's not that simple. It's somewhat challenging. I did write a lot of my thesis whilst observing at UCAT. So if anyone from UCAT is on the live stream, snaps, guys, I would not have graduated without you letting me not do a lot of some things that needed to be done so I could write my thesis. Love UCAT. Okay. Yeah, I wanted to touch a bit on, so there's anyone who's interested in learning about generally any of the other telescopes, I can do it in the Q&A because I know we don't have endless time. But I did want to touch on a couple of cool things that are up on the mountain. This is the coolest plant. It's unique to this particular elevation and Hawaii. It's called a silver sword. It looks like a freaking Pokemon. I love this thing, right? If you stand over them, I couldn't find a picture of this like showing this well, but if you stand over them, they almost look like they've been spray painted. They have this like residue that kind of spills out, and their life cycle is manic. Look at that. That's ridiculous. They kind of start as this little thing, and then they become a bush, and then a tree, and then a bush again, then a Pokemon. It's just the coolest thing. So if you ever get to go to Mauna Kea, there's a protected silver sword area while you're acclimating, so you don't get sick, like I did the first time, and just the once. While you're acclimating, you can go and see this. You can walk around it, and it's very, very, very cool. If you steal one, the police will chase you, and there will be an island-wide alert. I've seen it. They are endangered. Don't do it. That was on Maui while I was there visiting. Someone stole one, and then it was all over the radio. This guy has a silver sword, like, get it. I want to say they caught him. I don't know. Brave. Yeah, and also you can't talk about astronomy in Hawaii without touching on the cultural aspect of it. And we have this is actually a picture from 2019 when the TMT, or the 30-meter telescope, which I'm going to talk about in a minute, was slated to start building. That telescope has not been built. And a lot of this is a continued kind of conflict between some of the university personnel or some of the personnel who were dealing with the management of the mountain and the native Hawaiian community. It was managed very badly when it was set up, and the native Hawaiian community did not have the input they should have had, right? This is, I think, one of those small but very important examples of what is happening worldwide with the use of land that is originally not the people who are building on it, right? And I get a lot of questions. I wanted to bring this up now. Like, I'm not Hawaiian in any way, of course, so I cannot speak to this experience. But when we're building something on land that isn't originally the person who's building on it, indigenous land, doesn't matter if it's a telescope, a pipeline, a road, whatever, do we want that thing at the expense of the community? Because I say no every time, even when it's science. So, you know, that's an opinion, but this was from that protest. Since then, a new Mauna Kea Oversight Authority has been put in place, which is doing a really good job. It's majority Native Hawaiian run, and it has a really cool, there's an astronomy advocate on it who's a really, really good guy, and they're all working to steward the mountain together as opposed to having it be kind of ruled over by, you know, others. So anyway, this is the telescope that was meant to be built, question mark, asterisk, might go to Spain, the 30-meter telescope. Keck was 10, this is 30, right? This thing is absolutely gargantuan. And if you look on so I've put some examples up here. On the left-hand side, you see Keck, and on the right-hand side, you see TMT. This is Io, a volcanic moon of Jupiter. So, you know, that's just to show how pretty good it's going to get if we can do that. That's better than a lot of space telescopes. Very cool laser also. And I can talk a bit about the TMT if anyone's interested, but I'm just going to pop through these last few slides. Oh, where was my Atlas slide? Oh, did I go over it? Yeah. Thank you, Will. I'm going to touch on Atlas quick. Who knows what this is? This particular object. It's been in... Aliens. Yeah, you said it the right way, though. Thank you. This is not aliens, all right? Atlas is one of the two, there's a couple of different telescope arrays in the world, which are fairly small telescopes. This one's on Mauna Loa, but you have them all around the world, and that allows for what we call a 100% duty cycle, which allows you to observe all the time, right? Because it's never daytime if you have observations going on all the time. This particular one is designed entirely to find things coming and killing us, right? Not aliens, asteroids. And this one was discovered on, well, actually, no, this is a recent image, but I think it was about a year ago now, first seen. And there's been some conspiracy about it being aliens. It is not an alien, but I think it's a really interesting point because it is an interstellar object. And anyone who's kind of into that stuff will know that the first interstellar object was also discovered on Hawaii. It's called a Muamua, and it's here on the bottom here. A Muamua translates to visitor from a distant land. I'm butchering it. It's something way cooler than that. But it also, there's a couple of different words within it that mean like scout and traveler. And this is an artist's representation of a Muamua. When we found this one, it was an alien. Wasn't though, right? So this speaks to a really interesting and important element of science, I think, generally, which is the first time we find something, this was the first interstellar object ever, meaning it came from a different system than ours. Everyone got really excited, but now we see them all the time. And it's because now we know where to look, right? We know what we're looking for. And that's really, really cool. So then when we get conspiracies about it being aliens and such, I think aliens are real, it's just not this. It kind of devalues the coolness of what we're able to do now, right? The fact that we see these things like all the time, these things coming from different systems, that's incredible. So yeah, very, very cool, but not aliens. Thank you for noticing that, Will. I can't believe I went past it. Okay, this is actually, I think this is my last slide just because I threw it up because there was a couple of things I missed. For the mirror geeks in the room, because I am. On the right, this isn't just the mirrors from Mauna Kea. This is all the like perspective mirrors in the world. And this big, if you see this big like shaded donut thing, that was gonna be the overwhelmingly large telescope. That got canceled. We're real good at names. So the 30-meter telescope you see on the top right, and below it, the extremely large telescope. Don't laugh, that one's getting done. Giant Magellan is on its way, I think. And the ELT is being built. It's just not seen first light. TMT, yeah, question mark. But it's not the technology that's held it up, as we've discussed. So these are all, yeah, these are most of the kind of most in use telescopes. The James Webb down there on the bottom left is an example of this hexagonal mirror placement. I also just wanted to show on the left, this is Pauehi, which was the first black hole to ever be imaged, actually seen, right? So again, You're not seeing the hole itself, you're seeing the behavior of the things around it. And this was done through a worldwide process collection of radio and sub-millimeter wave telescopes. In the plot at the top, you can see which ones were involved. And I wanted to include it because 2 of the ones on Mauna Kea were, which was JCMT and SMA. So SMA is the Smithsonian one, which is an array of telescopes. And JCMT, James Clerk Maxwell Telescope, is a radio telescope, or sub-millimeter telescope. And they collaborated with people all over the world to eventually get this badass image of a black hole, which is called Pauehi, which is, oh man, I never want to say them because I'm always going to get it wrong. But anything that's discovered on Mauna Kea, which is that cool, goes to a committee and they think of a cool name for it. Yeah, I think that is all I have. I'm going to, oh no, one more slide. I've been showing these a lot recently in my slides. This isn't to do with Mauna Kea. I think it's important. This is the astrophysics fleet of NASA. These are the telescopes I think about when I'm using a space-based telescope. So I use TESS. I will use Roman. Kepler's not on here anymore. With the cuts that are projected, we're losing these. This is the planetary fleet. Same kind of thing. We're losing these. So I don't want to say my opinion on this, but I just like people to know what the reality of cuts to science are. And if I was giving my talk about wave bands, which I do a lot, you would see that here we lose like basically all of the X-ray. Chandra, which you see there in the middle, is the most productive space telescope of all time. So if we lose that, we lose data that hasn't even been looked at yet. So yeah, sorry to end on that note. I just think it's important to share that information. And I'm definitely happy for any questions at all that you have. Thank you. Ooh. I put the webcam up here that we can look at. This is the webcam from the summit right now, one of them. It's not nighttime, unfortunately, because of the time difference. So look, there's a cloud. Getting in the way of all our observations. You can't see the telescope I use, but the first telescope ever on the mountain, UH-88, is the one in the far right. And this is a QR code to my nonprofit. I also, like, Billy's like, we need money. I need money. So, don't forget to tip your local astronomer who wants to go to space and help autistic people get the jobs they want.
Yes, if y'all have any questions, we're going to pass around a microphone so that it can be heard by everybody, and everybody at home that's watching can hear the question. Oh, right up front.
Oh, I always dreamed that I wanted to be like an astronaut.
Amazing.
But, wait, my question is, do you know what Betelgeuse is?
What it is, or why
Betelgeuse.
it is. The star?
Yeah.
Yeah, so Betelgeuse is probably one of the coolest stars ever. That's a really good choice. We recently found out that it has a sibling, another star near it. So a lot of these conversations recently about it exploding and becoming a supernova was because of some changes in the light we were seeing from it. And now there's this discussion that maybe it's a separate star. Also a Mauna Kea observation, actually. That was Gemini, I think. But yeah, no, Betelgeuse is one of my favorites too. I love it. And you can be an astronaut. In fact, you will be an astronaut. Just do it. Why not? Yeah? Yeah, you can do it? Yeah, you are. All right. I'm watching. Anyone else?
Anyone else? Oh, right up front.
You showed just a slide or two before about the cuts, and these telescopes that are out in space. If there are cuts to them, is there any way to get them back at some point?
What they do is now I'm not, and again, all these opinions are my own. I'm also not a NASA employee, and all these telescopes are like under that umbrella, right? So that's like government work. But to my knowledge, what happens when you close out a space telescope is the idea is to close it out safely so that it can't be intercepted by anyone else or used by anyone else, especially if it's something like X-ray, right? That could be kind of nefarious. You do a bunch of processes to basically sever the link to it, and you get all the data you can, but you have to then store that data. However, if the mission is closed out, you're not allowed to use the data or look at it. It just has to be kind of put on a server in the never. So no, you cannot retrieve them. I know that you can retrieve well, there's a lot of space junk out there, and I know there's some arguments about retrieving that, but all of these kinds of satellites are too far out.
Other question?
Is there anything
Hold on.
that can be done to save them? Because this seems like sorry. Is there anything that can be done to save these telescopes?
Again,
like
call your
funding?
senators. Like, I'm not actually sure what the latest was because I got that slide from a friend, but I know it's all to do with the budget, right? And I'm not very up in the knowledge of the budget and how that works. That's not my area. But I do know that research funds are from the Appropriations Committee that also does justice. So that's an interesting duality. And that's to do with bipartisanship, I think, right? Like, you want like things to go through. I don't know. I don't know. Like, really, it's about arguing that it's necessary. And there's a lot of cuts to a lot of different areas of science. And of course, I mean, even I would argue that there are some that need money back before we do, right? Like, so I don't know. Call people, run for office, get into astronomy. Yeah, I'm sorry, I don't know. Be aware, I think, right? Anyone else? I'm sorry, that was a very depressing last slide. I should have ended with something fun. The video. Yeah, go on. Oh, do you know what? I just realized I can show something cool. I'm a galactic archaeologist, so my base research is in galactic archaeology, which is using the stars as a fossil record. So I think about how our galaxy formed and evolved by looking at stars in the distant past, the same way Indiana Jones looks at the past with like bones and artifacts and stuff, I guess. He's a bit cooler, isn't he? I'm going to show you my favorite webcam because it's not this one. It's not even a telescope, but it is near my house. This is the volcano currently. This is a Halima'uma'u crater, smoking up. It's been pretty eruptive lately. Sometimes I put this on in my classes and just let it, yeah.
Can you tell us why the ground-based telescopes have lasers?
Oh yeah, that's such a good question. So the atmosphere getting in the way, that's kind of the point. So the lasers that we use are designed basically to create stars in the sky, and I'll explain what I mean by this. When you have a turbulent atmosphere, so when you have a lot of stuff going on, which you always do, right, you want to try and subtract that out of your data. And we do this using a thing called adaptive optics. So this is using, like, basically moving your mirror, like with tiny bursts of air or whatever, to cancel out the turbulence in the atmosphere. Does that make sense? So if you cancel out the turbulence in the atmosphere, you subtract it from your data and you get a perfect image, right? But how do we do that if we don't have a star that's like nearby that we can use as super bright? We use a laser, right? So the laser makes what we call a artificial guide star, right? This is also a good time to have a conversation about space lasers. You could, in theory, use a laser in space as an artificial guide star for all 14 telescopes and save a lot of money. Lasers in space, for good reasons. Anyone else? Did that answer your question? Oh, awesome. Yes. How do you sniff planets? Oh, I love this. So a lot of what I do is photometry, so we just look at light. Well, all astronomy is light, but I just kind of collect a number. Spectroscopy is where you take the light and you split it up with a prism, right, into all its different wavelengths and colors. Think Pink Floyd, right? Why do I feel so much older than I am? It's because I'm like referencing all these bands from before I was born. Splits it up into all the different colors. All these different colors are different wavelengths. All these different wavelengths correspond to different elements, right? So it's all to do with energies and how elements are made up, electrons, and getting excited and things. And I'm definitely happy to explain that too. But when you look at a star and you break up its light that way, you can tell what the star is made of. To do it for a planet, you have to do something called transmission spectroscopy. And this is actually only done in space right now with a JWST. I think there are maybe 1 or 2 instances of this happening on Earth. But what you do here, and this is probably the coolest thing ever, you get the star and you wait until the planet moves in front of it, and then you take a picture through the atmosphere of the planet, of the star, and then you already know what's in the star because you've looked at it before. So you get rid of that, and what's left is the atmosphere of the planet. How cool is that? Right? Very cool technology. So we've now found planets have water, they have carbon dioxide, they have all sorts. Very, very cool. Yep.
Speaking of the adaptive optics, why in astronomy, when they are doing the wavefront sensing, they want to go to very high order aberrations, even more than 10th order?
Oh yeah? Got an adaptive optics engineer in the building?
Yeah, I work on wavefront sensing and
I love
optics, yeah.
I was in an office for many years with someone who built the first ever pyramid wavefront sensor, which was, we can talk later if you would like. I can talk about pyramid wavefront sensing all day because she would talk about it a lot, and that I'm not an instrumentation person, so all of this is from sitting in an office with an instrumentation person for 10 years. But the higher order aberrations it's going to matter. Oh gosh, you would always talk about this. I think that's why they ended up using the pyramid wavefront sensor, and that was at Keck. So that was because the more versions of the wavefront you had, the more you could subtract out. I can't remember, honestly. I could tell you if I could look at it. Do you know what I mean? Or we could talk about it later. Yeah. Or do you know the answer?
No, I don't know the answer.
Oh.
I know that it matters, the aberration. But
Yeah, it does, yeah.
Because they go very, very high order aberrations. For example, for fifth, we have 21 Zernike coefficients,
Yes.
but they go something like 300 Zernike coefficients. And
Right. Are we
I
ever
don't
going to get... I don't know if it's necessary, right? Like
yeah,
after
that's
a
the
point?
thing. I mean, I was wondering why it is.
So there's a couple of cool designs that have happened recently with, so for the people in the room who are not talking about Zernike polynomials, there's not just this one layer of stuff happening, right? There's a whole bunch of stuff happening in the atmosphere at different layers, and it's causing different aberrations. And this is even as simple as the inside the telescope dome versus outside the telescope dome. Right, so you want to open your telescope up as soon as you can in the evening to cool it down to the same temperature, because otherwise you're going to get, different heats of, when you go underwater like scuba diving, you see the hot water looks a bit different, kind of weird and flows through. So there's a lot of different ways to do adaptive optics. One of them that I think is really cool, is pretty new, is called ground layer adaptive optics, and that's where you use multiple sensors, but it's only to subtract out the bottom layer, and apparently that improves it like exponentially. But again, I left Hawaii before this became a thing, so I don't know. But I have a lot of friends who might know. Anyone else? Any more Zernike polynomials in the building? Yes.
Just curious, so you spoke about the TMT, the 30-meter telescope, and I'm curious about some of the pros and cons versus a single large versus multiple smaller. Because you can obviously,
multiple smaller telescopes, like an
right, like an array or
interferometer.
something. So, because if you had the array, right, you have the option of doing multiple targets with less aperture, but then you can
Basically
combine the
Keck,
aperture.
right?
And I'm just curious what why did they decide on a single 30 instead of multiple smallers?
Because there are ones that have multiple, right? Like Magellan, I think, is going to be 4. I think that is, I don't know, I'm not on their like design board or anything, but I think it basically comes down to your science cases, and there's some things that are going to be better with interferometry and some things that are going to be better with a single mirror. I know that the adaptive optics, for one, can be improved that way, but also I think direct imaging, like very good direct imaging, is better with one mirror in that particular wavelength. Like this is that I'd have to think about this. I'm not sure, honestly, because you're right. You can add things together, but there's a trade-off, right? Yep.
I think short wavelength light interferometry is incredibly hard to do.
It is incredibly hard
It's
to
a
do.
lot easier with radio telescope stuff with the long baselines. The large binocular telescope, for years and years and years, they're right next to each other. They couldn't get the images to merge.
Yeah, that was a shame. I liked that one. It looked like an owl. This gentleman's right. So with the arrays like the one that got Hawai'i, right, we're talking about very long wavelengths. We're talking about radio. We're talking about submillimeter. When we're talking about visual or infrared light, that's a lot smaller wavelengths, and it's a lot harder to do that, to do the math, right? Because the wavelengths aren't going to kind of cancel or occur the same way. So I think it's just basically a math or engineering problem. And I guess cost versus scientific output.
All right, if you have any
You guys
other
are
questions.
testing me. I love this. Also, I like the Starfleet T-shirt on this gentleman. Or is it Space Force? It's Starfleet. Yeah.
So if you have any other questions for Dr. Schonhut-Stasik, please hang around because she's going to be here for a little while. But let's give her another big round of applause for
Thank you.
a wonderful talk.
Thank you so much, guys.